All right, so this chapter is on inductance. So let me show you what this is about. You guys saw that, so this is the Maxwell's Faraday's equation. What this tells you is time-varying magnetic fields produce electric fields. Okay, so we'll see an application of that. So that's what this chapter is based on. So here's a here's a diagram. So let's say this is a circuit, and you pass a current through this circuit. So we're looking at it edge on. You pass a current through this thing, which is producing a magnetic field like that. Now, if you change this, vary this current with respect to time. So let's say you hook up an AC current to this thing. This magnetic field will change, which will induce a current in this coil. Okay, so this is how those inductive stove ranges work. Okay, so in the inductive stove, you guys know what I'm talking about? You guys are aware of inductive stoves? Okay, so what this is an inductive stove is you have an AC source hooked up to a coil. Okay, I got to do it better than. Okay, so here's a coil, and you put a steel pot there. Okay, so what's happening is this AC source is varying the current, is changing the current direction 60 times a second. So the magnetic field here is changing 60 times a second. Okay, and that induces a current in this pot, which heats up the pot. Okay, so that's how the inductive coil works. It's not heating this glass top, it's directly heating this pot. So these inductive stoves are 90% efficient. A gas stove is about 40% efficient. That is, the heat generated in the, by burning gas, only 40% of that goes into heating your food. An electric stove is only about 70% efficient. Because an electric stove there's a coil underneath which is heating the glass top, which is heating the pot. But the inductive coil is directly heating the pot. Yep. All right, so the title of the slide is mutual inductance. What this means is the following. Okay. What did we learn? A changing current in this circuit induced a current in this circuit, a nearby circuit. So you had a mutual inductance, okay. A coil nearby, an EMF was induced in this coil due to changing currents in this coil. Okay. And that's mutual inductance. All right, so this is how, like I said, inductive stove work. This is how wireless charging works. Okay, this is how transformers work. So this is an extremely important phenomenon. And in fact, this is how you learn these devices work. How do these devices work? Let's say you call me. How does this know?
It's to send a signal.
Yeah. What does that mean? So you're sending an electromagnetic signal which has a time-varying magnetic field component. This guy, and we'll talk about a tuning circuit. Okay. This guy has a coil that senses that changing magnetic field. Okay, and then you tease the information out of that signal. All right. So mutual inductance is how, like I said, inductive stoves work, transformers work. So the important application of one of the important applications is transformers. Yeah. All right, again, time varying currents in this circuit are inducing an EMF in a nearby circuit. Okay, so this equation says the EMF induced in coil 2 due to time varying currents in coil 1 is EMF induced in coil 2 is proportional to time varying currents in coil 1. So you guys see that. What if there's a steady current in coil 1? What is the EMF in coil 2?
Nothing.
Nothing. If di1 by dt is 0, that is, if you have a DC current here, the magnetic field is not changing, you're not inducing an EMF here. All right? So this proportionality constant is called the mutual inductance between these two, between circuits 1 and 2. Okay? All right. Now so here's what we did. Here's coil 1. Here's coil 1. We were changing the current in this coil 1. And here's coil 2, okay, which was inducing an EMF there. Okay, what will happen if you may take the two coils further apart? What will happen to the EMF?
A weekend?
It will weaken. So this proportionality constant will decrease. Okay. What will happen if you have more turns on this coil? If you increase the number of turns on this coil, it'll increase. What will happen if you take this coil? Here's the first coil. You're changing the voltage and current in this thing. Here was the second coil. And now if I turn this coil this way, what will happen to the EMF?
Zero?
It'll decrease. It'll almost go to 0. Okay, very good. All right, so you see that this mutual inductance depends on the geometry of the two coils. Okay, and in general, it's hard to calculate, but it's the proportionality constant. When current in the first coil is changing, the EMF induced in the second coil is proportional to the rate of change. And this proportionality constant is called the mutual inductance. So it depends on many things. It depends on how close the coils are, the geometry of the coils, and all that kind of stuff. Okay, but again, mutual inductance is important in inductive heating. Okay, wireless charging, transformers, and so on. Okay, so we use this phenomenon every day. So again, it's currents changing in one coil is inducing an EMF in nearby coils, okay, nearby circuits. All right, here's another interesting phenomenon, self-inductance. All right, so let's say you take a wire and connect it to a battery. So a resistor and connect it to a battery. Okay, well. Okay, so here's a switch. When I close the switch, what do you think will happen? I'm sorry? Yeah, so what I'm going to do is I'm going to close the switch at t equal to 0. And before I close the switch, the current was 0. And at t equal to 0, I close the switch. And what happens? A current instantly rises to its value. Okay. Now what we're going to do is we're going to take this wire and we're going to wind it up like this. Okay. We're going to wind it up into a cylinder, sort of around a cylinder. Okay. So now what we have given it is something called an inductance in addition to its resistance. You'll understand the symbol in a second. Okay. Now, if I close the switch, it's the same wire. Instead of having it straight, now I took the wire and wound it up around the cylinder. Do you think the current should behave exactly the same way? It's the same wire. I mean, you guys are all college educated. Should we behave the same way, right? Here's the property it assumes. So if you wind it up like that, when it acquires an inductance, now this configuration achieves the ability of fighting against changes in currents. Okay, so now the current, instead of rising instantly, now rises exponentially. It still goes to the same value, but it rises slowly. Okay. That is called self-inductance. Okay. All right, so here's this wire. Here's this wire. If you try and increase the current, so when you close the switch, you're trying to increase the current through this coil, and it doesn't like changes in current. Okay. And so it induces a self EMF in the opposite direction. Okay. It'll try and oppose this attempt at increasing the current. If you try to decrease the current through that coil, it will induce an EMF in the opposite direction, fighting that decrease in current. Okay. So a wire wound up as a coil acquires this ability to fight changes in currents. Okay. So an opposing self-induced EMF develops as current increases or decreases in an inductor. Okay. Okay, again, like I said, you take a straight wire. The straight wire doesn't care if you try and increase or decrease currents through it. You take the same wire and wind it up around a cylinder. Now this wire acquires the ability, it doesn't like changes in current. Okay? So the self-induced EMF is proportional to the time rate of change of current in the inductor. Okay, so you took a wire and wound it up like that. You try and increase the current, it will induce a EMF in the opposite direction. How long does this induced EMF last?
As long as the current's changing?
Very good. Okay, as long as you're trying to change the current. If the current is steady, this thing is zero. Okay? If the current was flowing in this direction and you try to decrease the current, then an induced EMF will be in the opposite direction to try and maintain that current. Okay? So this device does not like changes in currents. Okay? So, and that's called inductance. So for a closely wound solenoid of n turns, so this thing is called a solenoid, a closely wound solenoid of n turns, the inductance is mu naught, that's the permittivity of free space. N is the number of turns per unit length. L is the length of the inductor. A is the area of cross-section of the inductor. Okay? So this is the volume of the inductor. Okay? So that's the inductance of this coil. And the self-induced EMF is proportional to the time rate of change of current. Okay, and the proportionality constant is called the self-inductance. Okay. The negative sign just tells you that the EMF induced is in the opposite direction of the time rate of change of current. So if the current is increasing in this direction, the induced EMF is in the opposite direction. Okay. So the units of inductance are henries, after Mr. Henry, and it's volts per ampere second. Okay, volts second per ampere. All right, so again, what have we learned? That you take a straight wire and wind it into a cylindrical structure. What does it acquire?
Self-inductance?
it acquires self-conductance, which is the ability to fight against change in currents. Okay, and that's self-inductance. Okay, oftentimes you want to increase the value of the inductance of a coil, and you can do that by filling it with a magnetic material. And when you fill it with a magnetic material, this permittivity of free space is replaced by the permittivity of the material, and you can increase it by a factor of 100 easily. Okay? So, all right. So what is an inductor? An inductor is coil of wire. Okay? And we'll see what it does in a circuit. You already saw that, here's a circuit with an inductor and a resistor. If this inductor was not present and you turn on the circuit, if you close the switch, if this guy was not present, you close the switch, the current in the circuit rises from 0 to its steady state value instantly. With this guy present, the current now rises exponentially. Okay, so now we're going to show you that behavior. So you're closing the switch at time t equal to 0, and the current is rising like that. Yeah. And all this can happen depending on the values. The current is rising in a few milliseconds, okay? But that's what we're interested in. Yeah. So we want to study this behavior. Okay, we want to get an expression for the rise in current in this circuit. All right, you guys have all taken differential equations. So as soon as you see a system, what is it that you have not? All right, well, we're preparing you for differential equations. How's that? All right. All right, so as soon as you see a system, a physical system, what is it that you do? You chomp at your bits and you set up a mathematical model for it to study it. And the mathematical model is generally a differential equation. All right. So what we'll do is we'll close the switch, and for the few milliseconds that the changes are happening, you want to study the behavior of this system. Okay? Well, you close the switch, and this is a closed loop, and you know Kirchhoff's rule. What does Mr. Kirchhoff's rule say? Voltage rule say? That the sum of the voltages across all elements in a closed loop add up to 0. Very good. Okay? So that's what this is. All right, so we'll start here. You go across this guy, the voltage change is plus E. That's the EMF of the battery. And the current is flowing this way. Current is what we're interested in is current is a function of time. Yeah. This is what we're trying to find. So current flows from high to low. So minus ITR. So E minus ITR. And then see, since the current is increasing, this fellow is fighting that increase in current. So the induced voltage is positive in this direction. So it's trying to find, this is acting like a battery with the positive terminal there and negative terminal there. And so the change in voltage across this is negative L. L is the inductance of the circuit, of this device, times di by dt. Okay? So here's the differential equation modeling the behavior of this system. Yeah. And of course, you will learn how to solve these equations. Yeah. And so here is the solution to that equation. Okay, the current is rising exponentially. The time constant for the circuit is L over R. Tau, the time constant is L over R. And that's the scale on which things change. So after one time constant, the current has risen to 0.63 times its maximum value. After two time constants, about 90% its maximum value, and so on. All right, so let's look at the interesting part. At t equal to infinity, this term goes to 0, and the current is E over R. The steady state current is E over R, as if this guy was not even present. E over R is the current, which is what Ohm's law says. Okay? So what was this guy's job in the circuit? Just to slow down the increase in current, that's all. Okay? So the current in the RL circuit builds up exponentially rather than instantaneously as for a purely resistive circuit. All right, now we'll notice something interesting. It turns out that, if you go to one of the previous chapters slides, you'll learn. Okay, so let me take you back a couple of chapters. This is a capacitor. So here's a switch. When I close the switch, what happens?
Capacitor gets charged.
Capacitor gets charged. Yeah. And when the capacitor gets charged, you have an electric field. Okay. So what happened in this process? The capacitor got charged. Energy from the battery flowed into the capacitor, and energy is stored in the capacitor. Okay? And I don't know if you remember, but we talked about the energy can be thought of stored in the electric field. Whenever you created an electric field, you stored energy in the electric field. And it's an easy way to think about this. Here's the capacitor plate. This is positively charged, this is negatively charged. What do they want to do, the plates? They want to attract each other. And if you're preventing them from getting together, okay, so it's like a stretched spring, and you've stored energy in it. Okay. So anytime you've created electric fields, you've stored energy in the field. Okay. Similarly, if you go look at the previous chapter, if you have a current flowing through a solenoid, you have created a magnetic field inside the solenoid. Okay. So just like when you create electric fields, you're storing energy in the electric field. When you create magnetic fields, you're storing energy in the magnetic field. Okay. So that's what's happening here. When you establish a current through this thing, and a steady current flows through it, there's energy stored in the inductor. Okay? And we'll talk about that. So that's what we're going to see in the next few slides. Okay, once a steady current is established in the RL circuit, so initially the switch was over there, you passed a current through this, and a steady current is flowing through the circuit. And now what you're going to do is, you're going to flip the switch from A to B. What happens when you flip the switch from A to B? In the circuit. So when you go from A to B, what you're doing is you're removing the battery. Okay? When you remove the battery, okay, so let me go back to this circuit. Okay, so here's a plain old wire. I've connected it to battery, and there's a current flowing through this thing. And let's say by magic I make this battery vanish. What will happen to the current?
It'll go to zero, right?
Yeah, and instantly. Okay. So here, what we're going to show you is when you flip the switch from A to B, and you're making this guy vanish, the energy stored in there will drive the current for a little bit. Okay. So it won't instantly go to zero. Yeah. How long will it drive the current? And that's right. Very simple. Okay. So it'll drive a current till all the energy stored in the magnetic field is gone. Okay. All right. Okay. So again, now what we are doing is we're going to analyze the situation when we have flipped the switch from here to there. There's no more battery, and there's just this guy and this guy in the circuit. Okay. To analyze any system, what is it that you do? You mathematically model it, and generally there is a differential equation. Okay. How did we get this? Again, we used Kirchhoff's rule. We went around the loop, and the sum of the voltage changes across all elements should add up to 0. There were 2 elements, and there's the 2 terms in that equation. So let me show you that equation. So here's another depiction of this same thing. Initially, this switch was closed, and you had an inductor and a resistor, and a steady state current was established. And then what you're going to do is you're going to open this switch and close this switch. When you open this switch, the battery is removed, and when you close this switch, so you're doing it simultaneously, you're opening this switch and closing this switch. When you open this switch, the battery is removed, and close that switch. So initially the current was going in this direction, and you establish a steady state current, and then you remove this battery, and the energy stored in the inductor is driving that current. Okay? So this is what you're interested in. Okay? All right, so the current is in this direction, but the current is decreasing. Okay? Because this doesn't have an infinite store of energy. So let's start off here, or let's start here, and current goes from high to low. So IT times R, negative IT times R, and then you're going from negative to positive. So plus L times di by dt, okay, equal to 0, except that I is decreasing, so this guy is negative, and you want a positive term, so you make this negative L because I was decreasing. Okay, so it's ITR plus L di by dt is the equation. So there's the differential equation governing the behavior of I, which is that equation. All right, so again, you can solve this differential equation. This is a simple differential equation to solve. There it is. Okay, so the current is decreasing exponentially, and again, the time constant again is L over R. Okay, so the initial current at t equal to 0, this is 1. Initial current was the same as E over R, and then this current dies exponentially. So again, so this device stores energy in magnetic fields, and that's what we're going to show in the next 2 slides. Okay. So when you close the switch, okay, this device doesn't like increases in current. So as the battery is pushing current, as the battery is trying to increase the current, this guy is resisting. And anytime something is resisting, you are having to do work to do that. Okay. So, and the work done is stored as energy. So so if I lift this object up, what am I doing? I did work on this object, and that work done is stored as potential energy there. Okay. Why is it called potential? Because I can release it anytime I want. Okay. Okay, so the battery does work to establish a steady current, and in the process stores energy in the inductor. Okay. So again, once you close the switch, the behavior of this system is given by this differential equation. How did we get this differential equation again? using Kirchhoff's loop rule. Okay? So plus E minus IR minus L di by dt. Okay? I can bring these two terms to the right, and E equal to IR plus L di by dt. And then I'll multiply this equation by I. So E times I is I square R plus Li di by dt. What is this? This is the rate at which this device is supplying energy to this load. That's the rate at which power is being supplied. What is I square R? That's the rate at which energy is being dissipated here. And what is this guy? This guy can be written as d by dt of 1/2 Li squared. Okay. So the rate at which energy is being supplied by the battery, here is the rate at which energy is being dissipated in the resistor, and this is the rate at which energy is being stored there in the inductor. Yeah. So d by dt of this is the total energy stored in the inductor. Rate of change of that is the rate at which energy is being stored. Okay? So the energy stored in an inductor when a current I is flowing is 1/2 Li squared. Okay? So if you check your capacitors, the energy stored in a capacitor is 1/2 CV squared. And so this is that right? Yep. Capacitance is yeah. All right. So the energy stored in an inductor when it's carrying a current I is 1/2 Li squared. Okay. All right, so in a capacitor, energy is stored in the electric field when a capacitor is charged. And in an inductor, with the current flowing, energy is stored in the magnetic field. Okay. So in an ideal inductor, okay, if you consider an infinitely long inductor, most of the field is inside, the field is inside the inductor and uniform. Okay. And what we're going to show you is the energy stored per unit volume in this magnetic field. Okay. So here is the energy stored in an inductor. The magnetic field inside the solenoid is given by that mu naught. N is the number of turns per coil. I is the current. And here is the inductance for a coil, mu naught N square A L. And so if you substitute all those expressions, what you get is the energy stored is this fellow times AL. That's the volume of the inductor. So this is the energy stored per unit volume. Okay. So this is the energy stored in the magnetic field per unit volume. Okay. So what this expression gives you is, for instance, so you can calculate the following. So in this room, the Earth's magnetic field is pointing in this direction. So what this expression will give you is how much energy there is in the magnetic field per unit volume. Here is a meter cube. In this much magnetic field, Earth's magnetic field, the energy per unit volume is given by that expression. Yeah. So that's how, so the total energy stored in the inductor is energy per unit volume times the volume of the inductor. Okay. Which is equal to that. Yeah. So again, anytime you create electric and magnetic fields, you are storing energy in the fields. Yeah. So here's a transformer. Okay. We use this all the time. All right, so what this transformer does is, okay, so here's a coil. If you apply an AC voltage to the coil, this produces a magnetic field that is changing direction. And this soft iron magnetic material, what it does is it couples this magnetic field to this coil. Okay, it couples that strongly to that coil. Okay, so if the current changes, this magnetic flux changes, and that'll induce an EMF in this coil. Okay. So what's this useful for? So what's the transformer? What this does is the output voltage in this coil, the output voltage in the secondary coil is N2, the number of coils on the secondary coil, divided by N1, the number of coils in the primary coil, times V1. All right, let's do the following. Let's say this thing has 10 windings, and this thing has 10,000 windings. Okay. So, and we say we have 1 volt amplitude on the, okay, so V1 is, and again, this thing works only for AC currents, okay, so AC voltages, so V1T is 1 volt times, I guess, sine omega t. The amplitude is 1 volt, so the output amplitude will be, V2 will be, remember, 10,000, N2 is 10,000, and N1 is 10, times 1 volt. 1,000 volts. What's going on? So you put in a signal of 1 volt amplitude, and you got an output voltage of 10,000 volts. Sounds like free lunch to me. You can put in 1 volt and get 1,000,000 volt out with appropriate windings. All right, so what's going on here is the following. The input power is V times I. So, okay. And the output power, assuming no frictional losses, is the same. Okay. So if you step up the voltage, the current coming out is smaller, 1,000 times smaller. Okay. So why do we use these devices? If you go several chapters ago, so our electrical system is set up where, you have large producing stations thousands of miles away, and so here's a producer, and here's the consumer U, thousands of miles away. Okay. So you have to transport electricity through wires. Okay. And so the power transmitted is I square R. This is the transmission wires plus I square load. This is the transmission wire, I square load. Okay. So if you transmit power at large currents, the transmission wires are thousands of miles of wire. You'll lose a lot of your energy right there in transmission. Okay. Very little will trickle to your home. So very little will get to your home. How do you fix that? To fix that, you want to make this term small. Okay? So what you do is you transmit power at very low currents. Okay? So, but VI is the power transmission. That's the power. So you want to transmit power at low current and power, so you have to transmit at a very high voltage. Okay, so you producing power at Hoover Dam, and then you're transmitting power at 800,000 volts. Okay, so you have to step up voltages and then step down voltages. Okay, and that's what the transformers do. Yeah. So you guys have seen these transformers on trees outside your homes and stuff like that, well, poles. So what those guys do is they drop the voltage from, I think, 480 to 240. Yeah. And so there are several steps that go on. All right, so now we'll talk about these devices, okay, wireless devices, how all these guys work. All right, so let's talk about a device that you guys all understand and have seen before. So here's a mass attached to a spring. And if I pull this mass on to one side and let go, what will happen?
It'll oscillate
It'll oscillate. Okay? How long will it oscillate?
forever if there's no friction.
Forever if there is no friction. So if mu, the friction coefficient is 0, it'll oscillate forever. Yeah. So now let me introduce another device. What is this guy? A capacitor. What is this guy?
Your inductor?
An inductor. All right, so here's what we're going to do. Okay, so we're going to charge this capacitor and let go of this guy. And what will happen is this, it's charged like that, it'll drive a current through like this, and the current will flow, and then this plate will become positively charged. Okay, and then the current will flow in the opposite direction, and then again this will become positively charged, and then the process will continue. So when this thing is positively, this capacitor is charged and let go, current and oscillating current will flow back and forth. It'll oscillate just like this. Okay. And how long will this oscillate? Forever if there's no friction. And this guy will oscillate forever as long as there's no friction. And what provides friction is resistance. If there is no resistance in the circuit, this will oscillate forever. Okay. So here's the electrical parallel of this mechanical device. Okay. So this is the oscillator, and this is at the heart of all wireless devices. Okay. So that's how all wireless devices talk. Okay. So we have, how many of these circuits do we have in the world, you think?
Trillions?
Hmm?
Trillions?
There you go. Okay. So here's a circuit that are in the trillions, and we're learning about that. Okay. All right. How do you study the behavior of any system?
Different relations?
There you go. So let's set up a mathematical model for it. All right. So at any given time, there's energy stored in the inductor and energy stored in the capacitor. Okay. Here's the energy stored in the capacitor. Here's the energy stored in the inductor. Okay. There's no friction. What is happening to the energy? Is it dissipating? Is it decreasing? Is the energy of this guy decreasing? The total energy of this thing is constant, potential plus kinetic energy. So this is the total energy, and it's constant. So you take the time derivative of that, do the simple trick, and that should be 0. And so that gives you this I is related to the charge in the capacitor. I in the circuit is related to the charge in the capacitor, like that. Okay, so this gives you a differential equation for the charge in the capacitor. A second order differential equation. Okay, this is exactly like the differential equation for this. Xt is the, okay, d square xt dt square plus omega square xt equal to 0. If you go look at your notes, that's the differential equation for the position attached to the mass. It's exactly the same differential equation. This guy is omega squared. That's the angular frequency, okay? So the frequency at which this circuit oscillates is that 1 over square root of LC. That's the natural frequency of oscillation of that circuit. All right, so here's how wireless devices talk. Okay. So you send a signal, an electromagnetic signal, and if the frequency of this matches the natural frequency of this, which is that guy, we'll come to that bit in a little bit. Okay, that bit alters the frequency just slightly, but we'll come to that. Okay? So when you send a signal and you want to catch that signal, what you do is you tune the circuit. That's what this thing is about. See, this is a variable capacitor. So you're tuning, that's what a radio does. Your dial, you can change the capacitance, you're changing the frequency of this device and matching it to the signal. So in this room, there are signals from which radio station? FM, I'm talking about FM stations. There are signals from how many different FM stations in this room? Everybody and his brother. Okay. How do you catch the one you want? You're tuning your circuit, you're tuning the frequency of this thing to the 89.9 megahertz that you want to catch. Okay? Or you get tired of this, then you change this thing and catch 105.5 or whatever it is that you want to catch. When the frequency of this matches the frequency of the signal, this signal will set up a large current in the circuit. How about all the other frequencies? They set up very small currents when the frequency doesn't match. Okay, so that's the phenomenon of resonance. Okay? So when the natural frequency of oscillation of the circuit is this. Tuning circuits take advantage of this natural frequency with the phenomenon of resonance. Okay. All right, so again, so amongst all the signals, F1, F2, F3, the one you catch are such that you tune the circuit to match the frequency of the signal you want to catch. Okay? Of course, okay, how long will this oscillate? Forever. When?
There's no friction.
And there's no friction. Is there such a thing as no friction? All right, so we have to learn to deal with that. All right, so let's learn to deal with this. Okay, so this will oscillate forever if there's no resistance, but of course there's always resistance in life. Okay. All right, so what are we going to do to study this? Set up another differential equation. Okay. What does resistance do? What does resistance do? What does friction do?
It opposes motion.
Okay, what does friction do from an energy perspective?
Losses.
It converts kinetic and potential energy into heat. That's what resistance does too. It converts electrical energy to heat. Okay, so there's the energy stored in the inductor and capacitor, and this energy is converted to heat in the presence of a resistor. Okay, so the rate of change of this energy is that Okay, that's the rate at which the resistor is converting electrical energy to heat. Okay, so that's the rate at which this energy is decreasing. Okay, so again, you go through a little algebra, and there's the differential equation that's describing the behavior of the system. All right, so with resistance present, this circuit is governed by this differential equation, again, a second order differential equation. Okay. If resistance is 0, this term would be 0, and you would get back your original equation. You'd get back this equation. Okay. All right, so with resistance present, this is the equation, and you can solve that equation, and there's the charge on the capacitor, and you see there is the oscillation. It still oscillates, but the oscillation, the amplitudes is dying down. Just like that mass attached to the spring will oscillate, but its oscillations will die down. Okay. The new frequency, the frequency is altered. See, without the resistance, this was the frequency, okay, square root of that. With the resistance present, the damped frequency is slightly lower. Okay. And of course, if the resistance is large, if this guy matches that, then it won't even oscillate. Okay. So the critical value of the resistance is such that there's no oscillations for R critical. That is equal to that, and this will be 0. Okay. If the resistance is greater than that, okay, of course it doesn't oscillate. It won't even come back to its. Okay. In the spring case, if the friction is too large, you pull off the mass, and it won't even come back to its equilibrium point. Okay. All right. So here is the differential equation for with friction present, and this differential equation is very similar to that differential equation. Okay. All right. So that finishes this chapter. So let me summarize this real quick. Okay. There's a few important things we learned. Okay. So the first thing was you have a circuit, and if you have a time varying current in the circuit, it'll induce an EMF in nearby circuits. Okay, that's mutual inductance, and that's how inductive heating, wireless charging, and all those guys work, transformers. Okay. You take a straight wire and wind it up into a solenoid like that. Now this guy acquires the property of fighting changes in currents. Okay, this guy doesn't like changes in current. Okay, and that's called the self-inductance, okay, of the coil, and the self-inductance of the coil of a tightly wound coil is given by that, mu naught n square Al. Okay. Again, this device doesn't like changes in current. Okay, so what this guy will do is he'll smooth out currents in circuits. Okay, if there are current spikes, this guy will smooth out those current spikes. Yep. You saw that with an inductor present in the circuit, the current rises exponentially. Okay. And then we saw that in an inductor, energy stored in magnetic fields produced by the inductor. Okay. Mutual inductance is used in transformers, and here's an oscillating circuit. Okay, so an LC circuit will oscillate, and the oscillation frequency is given by 1/square root of LC. Okay, and this is at the heart of all wireless devices. Okay, so that tuning circuit is what's used in all wireless devices. Okay. So any wireless communication is done through that. All right, guys, so let's start.